And let's dive right into section 14. We're finally going into talking about Starlight. All right. So I've broken this up into about 4 sections. We're going to talk about star brightness, talk about stellar spectra, and what properties we can learn from that spectra, and then move on to the HR diagrams. So let's start diving into our material. Let's start with a simple question. All right. I'm going to say, let's say I have 2 stars. All right. And we'll draw this out. Let's say they are equal size to the best of my ability to draw stars. So they're roughly the same diameter or radius. Right? So we're going to have 2 stars. They're equal size, but they are different temperatures. And I'm going to say the blue one's the hotter star. I'm going to ask, relative comparatively, how does the hotter star radiation compare to the cooler star? I see some star, cool, bad puns coming in from the chat. Right. I'm seeing options of A is one of them. Right. Or A is coming in. Yes. Repeat. Okay, so repeat this. I have 2 stars. I've got 2 stars. They are the same radius, same diameter, but one of them is hotter than the other. And so what's happening is the hotter one, because it's hotter, remember, you glow energy. The hotter you are, the more energy you're radiating off. So the question is, well, how does that affect, say, the number of photons? And everyone seems to have gotten it. Yes. The hotter star is going to radiate not just more energy because it's hotter, but it's also radiating more photons. So the number of photons coming off this, what we're looking at here is a plot of the wavelength of light coming off, and basically the number of photons. So as you get hotter and hotter, you're giving off shorter wavelength photons. Shorter wavelength, higher energy. And correspondingly, the number of photons is starting to go up and up and up. So you're getting more photons radiation, and they're at higher and higher energies. So let's start talking about star brightness. And you've heard terms of like magnitude. So here's a great picture of this. We've got an asteroid, 65 Cybele. There's the asteroid. And it's labeled an apparent magnitude of 11.6. And here are 2 stars, HD 216932. It's got a magnitude of 9.1. And I go over here, HD 217121, apparent magnitude of 8.7. And you might notice they have these scales here, these apparent magnitudes, 8.7, 9, 11. These correspond to how bright they are. So let's start to tie all these concepts together. Take like that last picture. Let's say you're looking at a telescope, and this is the picture you see. You see a blue star and a red star. And the question I have for you guys is, which star is closer? I'm seeing a hard C. And there is no D option. All right. Soft C. All right. Everyone's picking up on this. All right. When we look at this picture, correct. There is not enough information to know what's going on in terms of the distance. All I see is the brightness, how big the star appears to me. And so there's a couple of ways to explain what we're looking at. So I'm going to rotate this picture. Every picture, there are 3 cases, so emphasis. This is the picture that we're seeing here on Earth. We look through the telescope and we can see this picture. Big blue, little red. Here are 3 cases of where those stars could be relative to us that all result in that same picture. They could all be the same distance, and one's just more luminous than another. They could have the same luminosities. The stars are equally luminous, but one's further away. And remember, the further an object gets, the smaller and smaller it appears. So they could have equal luminosities and just be a different distance. Or the most complex case, which is most likely what's going to be out there, is that they are different distances and different luminosities. You could have one star be a lot closer to us, but the other star is significantly more luminous. All three of these cases are going to result in the same picture for us here on Earth. So what if we had multiple telescopes? We will get into this. One idea, this ties in the concept of, could I have multiple telescopes taking pictures of these stars? And the answer is yes, that will definitely help. Two telescopes on the radius of Earth, basically we're on opposite sides of the planet, won't quite be enough to figure out these details for most of the stars universe. We'll talk about a concept where we use parallax, and we say, all right, Earth's over here at one time of year, measure out to the star. Now wait 6 months later, Earth has moved to the other side of its orbit. And there we'll stitch those pictures together to get these distances. So yes, using multiple telescopes is one way to expand our understanding of where the stars are at. So, we've gone over at least two of these definitions before, but I want to recap all of them together, all in one spot. So, you can have luminosity. So, a reminder, that is the total energy every second that is radiated by a star. The total energy. So, we're going to use this number a lot in later lectures. This won't come up again today, but we'll definitely see this value again when we start talking about other stars' luminosities. So when I say the luminosity of the sun, that's what the circle dot is. That's our astronomical symbol. L circle dot means the sun. And I'm saying the luminosity of the sun is equal to 3.846 times 10 to the 26 joules per second. And a quick side note, joules per second, some of you might know this. A joule per second is equal to the unit of a watt, 1 watt. And so when you're looking at your text or you're looking online, you might see these values reported in terms of watts or joule seconds. They're the same thing. Right? So basically, luminosity is how much energy every second you're giving off. How much are you glowing? Then we need to talk about brightness. And brightness is scaled by basically the distance. It's not just how much energy the star is giving off, it's how much that energy hits us in a given area. Imagine trying to sunbathe, right? You're getting a lot focused direct light, or is it scatter if it's long brought out? So you have to take into account the area. And so the brightness goes down with distance, right? And then new one, magnitude. Now I will point out that magnitude and brightness are very closely related to each other. They're very similar. Right? So the magnitude is basically the scale, and it's a measurement of the brightness. The magnitude, think back to the beginning of this bit, of this section. The magnitude is just going to be a number, 8.7, 11.2, right? It's just going to be a random number. It has no units associated with it. And the bigger the magnitude, lower the brightness, right? So I've got a table on the next slide. Hopefully that'll clear this up. So we talk about stellar magnitudes, all right? Let's go for Jupiter, Mars, right? These are the brightest planets in the night sky. Their magnitude is close to -2, right? Our sun is almost -30. And then you start going to the other side of the spectrum of this magnitude, right? Go to the faintest stars. Our eyes, our unaided eyes, we can see about a magnitude of 5.5, right? And more stars out there, the brightness goes down the further they are. And so the further away something is, the less bright it is, the larger its magnitude. So the larger the magnitude, the bigger the number, the less... Oh, come on, come back. Right. The larger the magnitude, the further away, or the less bright, right? Big magnitude, low brightness. Small magnitude, all right, we're into the negative. The more negative the number is, the brighter it is. So for our sky, the sun is the brightest object, which is why it has an apparent magnitude about -27. Now, closely related to this scale is the apparent magnitude. Related to that is what's called an absolute magnitude. Remember, brightness and luminosity are related to each other. Magnitude is a measurement of brightness. So what absolute magnitude does is rescale all of this, all these numbers, to as if every object was the same distance from us. Basically it says, take the sun, take the moon, Venus, Alpha Centauri, put them all 10 parsecs away from us and say, what would their magnitude be in that case? So this is, you could say, a fictitious number. It's a rescaling. Some scientists like to use this because this gives you a way to basically say the luminosity of the stars in one dimensionless number. Parsec. Parsec is distance. It's the distance of, if I have our sun sol, it's labeled a PC as a parsec. Hopefully this works. It's close to about 3 light. Let me double check the actual value. Let's see here. Yeah, 1 parsec is about 3.2 light years. So it's just a distance measurement. It comes from using parallax measurements, which we haven't talked about yet. We'll get to that around section 19. Right. So, an example of using this, right? Here is Sirius, right around here. The way you can find it, when you click on the picture, you zoom up on this. By the way, everyone, if you're following along the PDF, you should be able to click the images to link to wherever I got the figures from and see more information about them. So you can click, here is Orion's belt, over here is Sirius. Right. And so we have a relationship that can say, how can we compare brightness and magnitudes? So the way this works, take Polaris. Polaris, our northern star, has a magnitude of 2. Sirius has a magnitude of minus 1.5. Right. So going back to our idea of our magnitude scale, this is a lower number. It means Sirius is a brighter object. Sirius is brighter than Polaris. And so we want to compare these magnitudes versus their star brightness. Right. So what we're going to do here is say how much brighter is Sirius compared to Polaris. So we go to the formula, and I'm not going over the physics of where this comes from. This is actually an approximation, but it's a good one for our purposes. Right? I'm going to say, what's the ratio of brightness? How much brighter is Sirius compared to Polaris, the North Star? And it'll be this 2.5 raised to the difference in magnitudes. Right? Polaris is 2. Or sorry. Yeah, Polaris is 2. Sirius is a minus 1.5. So the difference in magnitudes is this 2.5 raised to the 3.5. And if you calculate that out, you'll find that this ratio, Sirius, is about 24.7 times brighter. Or another more straightforward way to say this. Sirius has a magnitude 1.5. Polaris is magnitude 2. Sirius is about 25 times brighter than Polaris. So the emphasis. Magnitude is just a different way to describe the brightness of the stars. And why do we still use it? Well, the magnitude scale was the first thing astronomers came up with. We have to go all the way back to the ancient Greeks. So, we can easily measure magnitudes. You just look up the night sky, take your telescope, and you say, well, how bright is that object? Magnitudes are easy to measure. Now I want to talk about how can we go from magnitudes to luminosities. So emphasis. First step. If you got the magnitude of the star, that's equal to its brightness. It's just another way of saying what's the brightness. Now the brightness, how bright something is, well, it's equal to its luminosity over the area of the sphere. Or emphasis, this equation here. The luminosity goes as 4 pi r squared times the brightness. So what's this image they're showing here? Imagine I've got this star. Here's the source. It is bright, Polaris bright in our perspective because it is closer. I'd have to double check which one's closer. It's about how luminous these stars are. Remember that game of saying which star is closer, which one's more luminous? It's a combination of both. One star could be brighter but further away, or it could be more luminous. It's a combination of their luminosity and their distance. All right. So, coming back here, I've got my star, my source, and it's radiating rays of light. So each red ray is a photon leaving this star. Now, if we're close to the star, give myself a given area. Remember the emphasis. It's the amount of photons per area. If I'm close to the star, then the area is getting bombarded with tons of photons. So the star is going to be very bright. Then let's say we're further away. The number of photons starts to go down. Increase the distance. Keep the distance up. Right? Same area. In all three slices, it's the same amount of area, but the number of photons shooting through that area is going down. And this is what I mean that brightness goes down with distance. The star is the same luminosity. It's still spitting out the same number of photons, but the number we detect goes down as we're further and further away. But, once again, here's the emphasis. If I have the brightness, right, and I know how far away the star is, I can calculate how luminous it is. Calling back to the beginning of this, we said, here's the picture we see. We see a bunch of different stars. We measure the brightness. From the brightness, we get from the magnitude, we get the brightness. If we can measure the distances, we can calculate how powerful these stars is. We can say, hey, this picture that we see here is equivalent to one star. The red star is 1 parsec away. The blue star could be 2 parsecs away. Orange is 3. Right? We do this combination of connecting the brightness and the distances to get how luminous the stars are. And no, we have not covered how to get these distances yet. Someone in the chat started to pick up on it. of using multiple telescopes. There's a lot of techniques. We'll have an entire section dedicated to how do we measure the distances to the stars. But for now, I'll just ask you to take, we know how to measure that. Can brighter stars block out dimmer stars? Absolutely. The brighter stars can block out dimmer stars. We could toy around with the position of these stars such that this guy is literally blocking anyone behind it. And that is a big question. Can you resolve the stars that are close together and one's brighter than the other? It's a huge issue that scientists are constantly tackling. So, from this work, these are things, this is about the range that we've managed to figure out. The least luminous stars in the universe, there's something of about 10,000 times less luminous than our sun. That's the, remember, L sun is the luminosity of our sun. So we found that a lot of stars can be 1,000 times weaker than our sun, or 10,000 times. The most luminous stars, they tend to be about 1,000,000 times more luminous than our sun. So the range here is that you can be 10,000 times less powerful than our sun, or 1,000,000 times more powerful than our sun. So there is a wide range of stellar luminosities. But one thing we have noticed is that the majority of stars are less luminous. Majority are not that luminous. And so a big open question is, why is that? Why are most of the stars not that luminous? So there's a question of, these luminosities, are they less bright than the moon? It's the property of that distance thing. Our moon is going to be significantly brighter than most of the stars. However, because of the proximity, the moon is not as luminous as them. And someone's nailed it in the questions. Does luminosity affect your lifespan? Absolutely. How luminous you are affects how long the star is going to live. And that ties into this question of, why are most stars not that luminous? Well, the most luminous ones burn out the fastest.